Chapter 22 of The Romance of Modern Manufacture. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Tim Neal. The Romance of Modern Manufacture by Charles R. Gibson. Chapter 22. Making Steel Rails. A network of steel rails is spread over the country, connecting all the towns of importance together, while the streets of busy cities have long stretches of tramway rails laid along them. Vast quantities of steel girders are used in our modern buildings, while engineers and shipbuilders require enormous quantities of steel bars, plates, and angle irons. Indeed, the use of iron in such forms is so continually in evidence that it will be of general interest to see the methods of manufacture. In the older methods of producing steel, the pig iron was melted on an open hearth, and in contact with the fuel, charcoal, it was exposed to a blast of air, so that the carbon in the pig iron might unite with the oxygen of the air. The carbon and the earthy matter contained in the pig iron were practically burned out of it, and a pasty mass of iron was left in the hearth. In order to let the air get at all the carbon in the iron, the contents of the hearth were stirred or mixed, and if the whole process was carried on long enough, there was only pure iron left. This pure iron was too soft for many purposes, so that the burning out process was stopped before the decarbonizing was completed, leaving a small percentage of carbon in combination with the metal. The amount of carbon left determined the qualities of the metal. If no carbon was extracted from the remelted mass, the result would be a brittle metal which we call cast iron. If the proportion of carbon left is less than 1/50th part, the resulting metal is called steel. But good steel may contain very much less carbon, while nearly pure iron is called wrought iron. Steel is intermediate to cast iron and wrought iron. Henry Cort, of whom we read in the preceding chapter, proved that burning the iron in an open hearth with charcoal fuel was not necessary. He showed that the hearth might be heated from below with coal, and the mass well stirred as before. Since Cort's time, this process of puddling has been greatly improved. If the pig iron being puddled contains sulfur, then some manganese ore is thrown into the molten mass to act as a physic. The sulfur leaves the iron to unite with the manganese, for which it has a strong affinity. Mechanical tools or stirrers have been introduced to make the process of puddling easier. After the carbon, or a large portion of it, has been burned out of the iron, there remains a pasty mass, which the operator rolls up into balls suitable for withdrawing from the furnace. It occurred to Henry Bessemer, a civil engineer in England, that if he could cause air to be blown through the molten mass of pig iron, instead of merely stirring the iron in the puddling furnace, he would be able to get rid of the carbon in the iron more economically. When Bessemer made his first experiments, he was alarmed somewhat at the phenomena which occurred. Melting some pig iron, he had it poured into a large cylindrical vessel. At the foot of this vessel there were a number of holes, or nozzles, through which a blast of air was forced by a blowing engine. One might imagine that the liquid metal would flow into these holes, which were about half an inch in diameter. But the blast was turned on before the metal was poured in, and the force of the air issuing from the nozzles prevented the iron entering them. The first surprise was that the temperature of the molten iron was greatly increased, although only cold air was forced through it. The chemical combinations which took place evolved great heat, and Bessemer was so impressed with this that he straightway read a paper to the British Association, entitling his paper on the manufacture of iron and steel without fuel. Of course, there really was fuel, but this was contained in the pig iron itself. The carbon in the iron united with the oxygen of the air forced through the mass, and this chemical combination formed a true combustion. Some alarm was felt at first, for at one point in the process a roaring flame rushed from the mouth of the vessel and produced quite a volcanic effect. Then, beautifully colored flames changed to a voluminous mass of white flame. This blazing of a Bessemer converter is seen in the illustration facing page 240. It will be observed that the Bessemer converter is on trunnions so that it can be tipped over like a tea kettle, and the converted steel allowed to flow into molds to form steel ingots. Although Bessemer steel will not do for many purposes, and has been superseded largely by other methods, the value of Bessemer's invention has been demonstrated by the fact that one Bessemer rail lasted longer than 20 iron rails. One drawback in connection with the Bessemer process was that the operators could not tell exactly at what point they should stop the process of decarbonization in order to leave the proper quantity of carbon in the metal. But Robert Michet, whose name is well known in connection with the making of steel, suggested a very simple way out of the difficulty. The metal was decarbonized completely. Then a quantity of good cast iron, Spiegeleisen, containing the proper amount of carbon required, and also a percentage of manganese, was added to the molten mass. In this way, the amount of carbon in the finished steel could be determined with great accuracy. In another process, which is interesting to see at work, the air is not blown through the mass, but flames of highly heated gas are made to play over the molten metal contained in a shallow hearth, the bed of which is formed of infusible sand. The heat of the waste gases is utilized to heat the perforated brickwork of the chambers through which the air and gas are passed. There are 4 of these brickwork chambers, and while the air and gas are passing through 2 chambers, the waste gases are passing out through the other chambers, and when these are sufficiently heated, the route of the air and gas is reversed, so that they enter by these heated chambers, leaving by the others which have cooled to some extent in heating the incoming air and gas and so on. This class of furnace is known as a Siemens-Martin regenerative furnace. It is interesting to watch one of these furnaces at work on a dark night. The men have to keep throwing in lumps of iron ore and occasionally limestone if the slag gets too thick. A man pulls the lever which raises one of the furnace doors, and looking through blue spectacles, one sees a white-hot lake of molten metal. When the smelter throws in a large lump of iron ore, there is a splash of liquid gold. Indeed, to stand and watch these men throwing these heavy pieces in the furnace reminds one of the days when as boys we lifted large stones and flung them into a pond or lake, hurrying back to escape the splash of water. After this real inferno has been at a white heat for several hours, the molten metal is run off into a huge ladle which rests on a railway trolley. This trolley carries the ladle to a row of heavy metal molds, each standing over 6 feet in height, and looking not unlike so many overgrown cowbells. The bell mouth of each mold rests upon a metal floor, and when the metal is poured in at the top of the molten mass becomes solid the moment it touches the cold iron base. In less than an hour, the bell-shaped mold is lifted up by a crane, and the heavy steel ingot is left. These may weigh as much as 10 tons each, but an average will be about 3 tons. These are stored till required. When it is desired to convert one of these ingots into rails, girders, or angle irons, the ingot is placed in a furnace which is sunk in the ground. This furnace is called a soaking pit, the idea being that the heat must soak through and through the great mass of metal, and not produce a mere surface heat, After about an hour's lodgment in this subterranean furnace, the white-hot ingot is lifted out by an overhead crane, which carries it through the air to a cogging mill. This mill might be described as a gigantic steel mangle with irregularly shaped rollers. The spaces between the rollers form large grooves of different dimensions. When the crane lays the ingot on the ground, we are surprised to see this white-hot monster make a sudden rush toward the rollers of the mill. Then, hesitating for a moment while the heavy rollers get a grip of it by the nose, the ingot passes through the widest groove, reappearing at the other side of the mangle somewhat longer and correspondingly smaller around its square waist. The heat from this glowing mass of metal is intense, and although it weighs several tons, it is handled by this great iron giant as though it were a mere toy. Powerful steel fingers appear from the ground and turn the heavy mass over on its side, while two large arms gently place it opposite any desired groove in the great rollers. The one-time ingot is passed and repassed through this great mangle, until the 6-foot ingot is now about 40 feet in length. It is now in the form of a heavy bar of regular shape, only its nose and tail being a little irregular, where it entered the cogging mill in its journeys to and fro. The man in charge desires to cut off these irregular ends, and when he pulls a lever, we see the long beam move forward and place its head below a powerful guillotine. A heavy arm descends and clamps the beam in position, while the beheading knife cuts through the great mass of iron as though it offered but little resistance. After cutting off the irregular end, the guillotine divides the long iron beam into 2 parts. One of these red-hot monsters leaves the guillotine and goes scampering over the ground to a great distance. Watching it in the darkness, we see this fiery monster halt for a moment, swing around, and then go off in another direction. Just as the red-hot beam left the guillotine, a very heavy gong was sounded to give warning along the route, for it would be fatal to be overtaken by this fiery serpent. The method by which the great beam is propelled along the ground is interesting. Along the whole route, there is a continuous series of rollers, placed across the path, only a few feet apart from one another, and sunk beneath the ground level so that the tops of the circumferences of the rollers stand up a little above the ground. The beam lies on the tops of these live rollers, which are driven round by means of bevel gearing on a long driving shaft at the side of the path. It is an impressive sight to see the men in charge controlling all the movements of the great mass of iron, making it go through the mill, first in one direction and then in the other, turning it on its side and then on that. All the energy supplied by the men is to move the hand levers, and these movements control the hydraulic machinery which handles the metal. Other levers serve to control the steam engines which operate the mill and the live rollers. The power required to drive one of the mills for rolling heavy girders in the works of the Lanarkshire Steel Company, Scotland, is obtained from a huge steam engine of close upon 10,000 indicated horsepower, and this prime mover is so well balanced that it can race its crank round in one direction, stop very quickly, and then reverse. When the second length of red-hot iron beam is about to leave the guillotine, we make our way along the side of the road it is going to take. The clanging of the great gong warns us of its approach, and as it rushes past, we feel the intense heat radiating from it. By the time we overtake it again, we find that it is passing to and fro through another smaller rolling mill. First of all, it goes through what is called a roughing mill, which roughens the surface so that the rolling mill with its specially grooved rollers may get a good grip on it. In this mill, the metal beam gradually assumes the shape of a rail, a girder, or an angle iron, according to the formation of the rollers between which it passes. As the metal beam passes to and fro through the rolling mill, it goes through grooves of decreasing size, so that they reduce its section, at the same time increasing its length enormously. It so happens that the rolling mill, which we are watching at work, is arranged for making bars of angle iron, which does not require so much metal per foot as a rail or a girder. By the time the rolling mill has squeezed the red-hot iron into the finished angle iron, the 20-foot heavy bar which arrived at this mill will measure about 200 feet in length. Indeed, there is not room for it to run back in a straight line along the live rollers, as the road has a bend in it. So the end of the long red-hot bar runs up an inclined chute towards the roof, and if necessary, out through the roof. It is strange to see this great red-hot monster rushing up the chute, and then sliding down again, as its distant end re-enters the rolling mill. As soon as the squeezing rollers have got to their closest position, the formation of the angle iron, or the rail, is complete. The accompanying diagram will give some idea of how the rollers squeeze a length of steel into the form of a rail. It only remains to cut the long bar into suitable lengths. The bar runs forward and stops for a moment, while a large circular saw approaches it and cuts off the irregular end. The red-hot bar then moves forward any desired distance, and that length is cut off in similar fashion, and so on till the whole length is divided up. When these circular saws are at work in the dark, they look exactly like the Catherine wheel, fireworks with which boys play, and which produce a fine circular display of sparks. Only those who have some idea of the older methods of working iron can appreciate fully the enormous saving accomplished by modern machinery. In the old days, the metal had to be handled in much smaller quantities, and it had to be lifted about from one operation to the next, requiring to be reheated between the processes. We have seen that the 6-foot ingot, after leaving the soaking pit at a white-hot heat, still remains red-hot when rolled out to 200 feet and cut up into the finished lengths. This is only accomplished by the mechanical means of handling the mass of iron. It rushes from one mill to another in a most businesslike fashion, and in about a quarter of an hour from the time the ingot leaves the soaking pit, it has been transformed into rails, girders, or angle iron. In closing this brief description, it may be mentioned that the quality of the steel is not arrived at in any haphazard fashion. Expert chemists analyze the materials from which the steel is to be made, and then determine the ingredients for the furnace. In many works, even the structure of the finished metal is examined by means of very powerful microscopes. End of Chapter 22. Read by Tim Neal, May 1st, 2023.
Chapter 23 of The Romance of Modern Manufacture. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Manufacture by Charles R. Gibson. The Railway and the Locomotive. The ambition of many a boy has been that he might some day become an engine driver. There have been other ambitions. I know of one little fellow who hoped he might be a coalman, the idea being that he might go about with a black face without the fear of his nurse chasing him around with a sponge and towel. Another little friend told me that if he grew up a gentleman, he was going to be a clergyman, and if he grew up a workman, he was going to be a carpenter. However, I believe that if a plebiscite had been taken of all the ambitions of the boys of a quarter of a century ago, the engine driver would have come out at the head of the poll. The suggestion of having a steam locomotive was a natural one after the success of Watt's steam engine. Indeed, Watt himself describes a steam locomotive in a patent which he took out in 1784, although he never put the idea into practice. Many people are under the impression that the idea of a steam locomotive originated in the mind of George Stephenson, whereas a practical steam locomotive ran on the streets of Paris before Stephenson was born. It is true that this locomotive of Nicolas Cugnot, 1769, attained only an average speed of about 2¼ miles per hour, about half the speed of a man walking at an ordinary pace. Yet it was the first steam locomotive on record. The first idea was that locomotives should run on the ordinary roads, and there were many successful locomotives of this kind prior to Stephenson's time. In most of these cases, the locomotive was a complete carriage, just as modern motor cars are, but as early as 1803, the idea of having a separate locomotive to draw carriages after it was quite definite. I refer to a very curious-looking locomotive built by a clever but eccentric Englishman, Richard Trevithick. Trevithick's engine was successful in drawing wagons containing 10 tons of iron at a rate of 5 miles per hour, but the inventor did not follow up his success. The best engineers of that time did not believe a locomotive could gain any great speed or climb a hill unless it were provided with a cogged wheel to work on a corresponding rack along the rails. We have a rack railway today, but that is to take a train up a mountainside in Switzerland. Trevithick's engine ran in South Wales when George Stephenson was 22 years of age, and this was 23 years before Stephenson's famous rocket was built. Railways had been in existence for the purpose of taking trainloads of coal from the collieries to the shipping places for 200 years, but horses had been used for drawing the wagons. Railways had come about in a very natural way. About the year 1600, the colliery owners laid down tracks consisting of a double line of wooden beams upon which the wheels of their carts might run. A horse which could draw only 1,700 weight of coal over the bad roads of those days was able to draw as much as 4,200 weight on the wooden rails. A flange was added to the rails to keep the wheels from slipping off, and permission was got from farmers to lay these wooden tracks across their fields, a rent or way leave being paid for this privilege. People were content to work away with these wooden railways for 100 years. But about the year 1700, long slips of iron were fastened to the wooden beams to prevent wear and tear. Some 40 years later, cast iron rails of the same form as the wooden ones were brought into use. We often find these flat cast iron rails in the neighborhood of collieries at the present time. It was the introduction of these cast iron rails which suggested the use of crossbeams, or sleepers, to give a proper foundation for the rails. And finding that horses could draw such great loads upon these railways, the increase in the size of the wagon became so great that the idea of making smaller wagons and linking them together occurred to the colliery owners. These flat cast iron rails would soon get filled up with stones and dirt and so the next improvement was to put the flange upon the wheels instead of upon the rails, and this allowed the broad rail to be dispensed with, and the well-known edge rail to be used in its place. Having traced the simple evolution of the railway, it will be of interest to see the advent of the steam locomotive. The eccentric Trevithick was the first to run a steam engine on rails, but we have seen that nothing further was done for about 20 years. In the interim, George Stephenson had constructed a primitive locomotive which ran on a colliery line at a walking pace, which was no better than a horse could do. It could draw about 30 tons, but a number of horses could do this for about the same cost. In making a second locomotive, Stephenson hit upon a good idea. He turned the waste steam into the chimney or funnel in order to increase the draft. This proved a very great improvement. The fire burned so vigorously that the quantity of steam was greatly increased. The next point of interest was the opening of the Stockton and Darlington Railway, 37 miles, which was one of the first to carry passengers. Most of the passenger trains were drawn by horses, but steam locomotives were used for goods traffic. Then followed the Liverpool to Manchester Railway in 1830, which was originally intended for horse haulage. George Stephenson was the engineer for the laying of this line, and he persuaded the directors to make an attempt with steam locomotives. They offered a prize of £500 if they could get an engine that would run at a rate of 10 miles per hour and not weigh more than 6 tons. It is well known that George Stephenson's rocket carried off the prize and attained the alarming speed of 29 miles per hour. It is difficult for us to realize the surprise of the people who saw the rocket attain so great a speed. The most learned men of that time had declared that it was palpably absurd and ridiculous to suppose that locomotives could ever travel twice as fast as stage coaches. It is amusing to turn to the quarterly review of a few years prior to Stephenson's great achievement. In the issue of March 1825, we find the following sentences. It is true that we who in this age are accustomed to roll along our hard and even roads at the rate of 8 or 9 miles an hour can hardly imagine the inconveniences which beset our great-grandfathers when they had to undertake a journey, forcing their way through deep miry lanes, fording swollen rivers, obliged to halt for days together when the waters were out, and then crawling along at a pace of 2 or 3 miles an hour, in constant fear of being set fast in some deep quagmire, of being overturned, breaking down, or swept away by a sudden inundation. As to those persons who speculate on making railways generally throughout the kingdom, we deem them and their visionary schemes unworthy of notice. The gross exaggeration of the powers of the locomotive steam engine may delude for a time, but must end in the mortification of those concerned. We should as soon expect the people of Woolwich to suffer themselves to be fired off upon one of Congreve's ricochet rockets as trust themselves to the mercy of such a machine going at such a rate, 18 miles per hour. We trust that Parliament will, in all railways it may sanction, limit the speed to 8 or 9 miles per hour, which is as great as can be ventured on with safety. We can imagine what the writer of the foregoing article would have said had anyone dared to prophesy a speed of 60 miles per hour with an occasional short dash of 90 miles per hour. We know that electric trains have beaten these records of the steam engine, a maximum of 130 miles per hour having been attained. From the illustrations facing pages 286 and 296, it is apparent that the early locomotives were mere toys compared with our modern express engines. The making of railway locomotives is now a great industry. We find thousands of men employed in individual works, all busy making and fitting up these great iron horses. Of course, the starting point is in the brain of the designer. He has to build the engine in imagination, and after he has made his drawings, he can test the working of the moving parts by means of a large model fixed to the wall of the designing room. He can lengthen or shorten the crank and levers in this large model to agree with his drawing, and by watching the valves when the crank is rotated, he can satisfy himself that everything works out as he expected. He then sends his drawing down to the tracing room, where a large number of young ladies are employed making careful tracings of the original drawings. These tracings are not to be handed out to the workmen, but are to be used as negatives for obtaining photographic blueprints. The old plan of making these prints was to place a piece of sensitized paper under the tracing and expose it to sunlight, just as one does in printing an ordinary photograph. The paper used has been prepared with ferrocyanide, which, when exposed to light, becomes blue, except upon those parts which have been protected by the lines on the tracing. This process of daylight printing often proved very inconvenient. It was slow, and then one could not get the sun to shine when required. The present method of copying these tracings is to have a large upright cylinder within which there is a powerful electric arc lamp which travels automatically up and down the cylinder continuously, while the tracing with the sensitized paper beneath it makes a journey around the cylinder, entering at one side and coming out at the other. The whole printing will take about 1 minute, whereas with the older method one had to wait at times, somewhat impatiently, for half an hour till the fickle sunlight would do the same work. These blueprints then go to men who prepare the work. Some prints will go to the pattern makers, who will construct the wooden patterns to enable the molders to form the sand molds in which the iron and brass are to be cast. Other blueprints will go to the shop in which the templates are made. When a young lady is desirous of making for herself a fancy blouse, she buys a paper pattern showing the shapes of the different parts required. She places these paper patterns upon a piece of cloth and cuts around the shapes. The engineer works upon a similar plan for cutting out and shaping many parts of his engines. Instead of making his patterns or templates of paper, he makes them of substantial sheet iron. These are marked off carefully, indicating where holes are to be drilled, and so on. The template for the frame of a locomotive is an immense thing, being, of course, an exact pattern of what the actual part is to be. We need hardly enter the foundry for the general principle has been explained already in connection with the making of sewing machines. But in the locomotive works, the castings are on a very much larger scale. The casting of the large cylinders for an express locomotive is no light undertaking. The same remarks apply to the forge, but it is of interest to see how the larger pieces of iron and steel are handled. When we see a huge bar of iron of about a 1-foot square section being withdrawn from a furnace to be hammered into a definite shape, we picture the village blacksmith trying to tackle this job. The energy that a man would have to expend would be enormous. Indeed, he could not hope to make much impression on so large a mass of metal. Compare this with the duties of one of the boys who operate the powerful steam hammers at work in this forge. It has seemed to me a very curious fact that almost every boy, while at this work, sits with his legs crossed and one hand in his pocket, as though this attitude had been arranged by way of contrast, while with his other hand he moves a light lever up and down, each motion being imitated by the great steam hammer, whose powerful blows soon shape the mass of metal into any desired form, or it will weld one shaped piece to another, and so on. A steam hammer is simply a strong piston working up and down in a steam cylinder, the inlet of steam being controlled by the boy already referred to. The free end of the piston forms the hammer head. This powerful tool, as we know it today, was invented by Naismith of Manchester in 1839. Another hard-working tool is the hydraulic forge, or press, such as shown in the illustration facing page 216. Some hydraulic presses are made to exert a pressure of 30,000 tons, though the locomotive builder will probably find one of 12 to 1,500 tons pressure sufficient for his heaviest work. The hydraulic press, as its name implies, does not deal out sharp blows like the steam hammer, but exerts a slow pressure, bending great plates of iron into the forms desired. A flat circular plate of iron is heated and pressed by a mold into the well-known form of the dome upon the top of a locomotive boiler. It may happen that some special shape has to be formed for which the engineers possess no mold. Suppose it is a certain size of plate to be bent up at right angles around the four sides. In this special case, a number of smiths attack the heated plate with heavy wooden mallets, which will not mark the metal, but by the time 4 smiths have finished one piece, the hydraulic press, if it had the proper mold, would have accumulated quite a pile of similarly finished parts. In constructing the boilers, a large number of rivets are required, so the making of these is undertaken by an automaton, which does not feel the monotony of always doing the one thing. Long bars of round metal of the dimensions required for the shank of the rivets are heated in furnaces and then placed in the rivet-making machine. The bar keeps putting its head under a guillotine, which cuts off the required length. These short pieces, while still red hot, are placed in a revolving carrier, which whisks the rivet under a small steam hammer, and with one smart blow this hammer forms the well-known rivet head. Much more wonderful are the machines which make screwed bolts and similar things. These machines are perfectly automatic, one man acting master to as many as 5 machines. He merely hands them each a long bar of steel and watches that they do their work satisfactorily. He gives one machine a long hexagonal bar, which the machine undertakes to convert into special bolts. These are to have hexagonal heads, plain round necks, and they are to be screwed along the remaining 3/4 of their length. The machines are really automaton lathes. When the machine feeds in the long bar, a finger comes forward from the opposite direction and pushes the bar back till exactly the correct length is exposed from the feed. One tool then cuts away the hexagonal circumference of the bar, making it nice and round, and leaving only sufficient of it hexagonal to serve as a head for the bolt. Then another tool cuts into the bar just beyond the head, but at this stage it refrains from cutting it quite free. Another tool comes into action and puts the desired screw thread upon the bolt, and as soon as this has been completed, the cutting tool again approaches the head and severs the bolt from the long bar. The machine then feeds in another few inches of the hexagonal bar and proceeds to make another similar bolt. Other automata are busy making those shapely studs which support the handrail along the side of the locomotive, and so on. It is quite strange to see a large number of such machines, each working away at its own job, changing its tools as required, completing one article and then commencing another, doing all this on their own account, while their master, the workman, is engaged attending to something else. The amateur carpenter very soon learns to plane and saw wood, but if he desires to work upon pieces of iron instead of wood, he finds that he must exert a great amount of energy. The practical engineer does not worry about the energy required to plane or saw large pieces of iron. He simply hands the work over to a machine to do all the necessary hard work. In one class of planing machine, a traveling carriage or platform carries metal to and fro under a fixed plane, while in others the work is stationary and the planing tool travels to and fro. I mention these facts as one sees those planing machines so often at our industrial exhibitions. When these machines have a revolving cutter not unlike a garden mower, but solid, they are called milling machines. Then there are different kinds of drilling machines, but these have been referred to in the chapter on sewing machines. Each mechanic receives his work all marked off so that he can place it in the machine in its proper position to be drilled, planed, slotted, or whatever else is required to be done. Each workman does some little towards the completion of the great locomotive. One lot of men have been making the parts required for the cylinders, and when these have been fitted together, the complete cylinder has to undergo a series of severe tests. First of all, it is filled with water under great pressure, and then it is tested with steam, and when quite satisfactory, it is handed over to the erecting shop. Other men have been busy making the different parts of the boiler, and these are dealt with in similar fashion. The making of the wheels has employed other gangs of men. The wheels are made of cast steel, and as the rims are to be subjected to very great friction, it is necessary to have them as hard and tough as possible. Just as the wooden cartwheel has a metal tire put around it, so the steel wheel of the locomotive is also tired. The tires for the locomotive are made of special steel, and they are put on in the same way as the blacksmith adopts in dealing with the cart wheel. In the case of the locomotive, the heavy steel tire is laid upon the ground with a circle of gas jets playing upon the metal circumference. When the tire has expanded sufficiently, the wheel is placed within it and the heat is withdrawn, whereupon the tire contracts gradually and takes a great grip of the wheel. It is afterwards fastened further with metal bolts. When the wheel becomes worn, it is sent to the repairing shop to have a new tire put upon it. In the erecting shop, there is necessarily a great deal of manual labor, although even here many automatic tools, driven by compressed air or by electric power, are brought into play. Needless to say, the building of a modern railway locomotive is carried out on scientific principles. The different parts are each made of the particular quality of iron or steel best suited for the purposes the parts have to serve. It is surprising how a very small variation in the composition of the iron may alter entirely its distinctive properties. The means of producing different qualities of iron and steel have been dealt with in the chapter on the manufacture of iron. It is a curious thought that these great express engines which race across the country with us are composed of little invisible molecules of iron, and that the stability of the whole frame and of the going parts depends entirely upon the natural clinging of these molecules to one another. In the molding shop, the intense heat of the furnace sets these little molecules vibrating at such a rate that they could no longer hold on to one another. The molder seized this opportunity of placing them in a mold of the shape he wished them to remain when they once got into grips with one another again. In the forge, the same method was used, but as the molecules were not freed sufficiently to lose all grip upon one another, some energy had to be expended to force the molecules into new positions. Hence the use of steam hammers and hydraulic presses. As we fly across the country in our fast express trains, we are trusting our lives to those ultramicroscopic molecules, each doing its duty and holding firmly on to its neighbors. Needless to say, each locomotive is severely tested before it leaves the builder's hands. The locomotive is first of all placed so that its driving wheels do not touch the rails, but rest upon the circumferences of other wheels. In this position, all the going parts of the engine may be tested while the locomotive remains stationary. It can be made to record its speed and its tractive power. Then, when all is considered satisfactory, the locomotive is allowed to go on its own wheels, and after being tested upon short tracks in the builders' yards, the locomotive is sent out onto the public railway, or, if it is to go abroad, it is taken to pieces and packed in cases. End of chapter 23.
Chapter 24 of The Romance of Modern Manufacture. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Manufacture by Charles R. Gibson. Building a Ship. We all know that ships are not modern inventions. They have been going about on the surface of the seas of this planet for thousands of years. The evolution of the ship from floating rafts and from canoes cut out of solid wood was quite natural. Not content with depending upon the fickle wind, the ancients propelled their ships with oars. Doubtless we have all had vivid imaginings of the galley slaves of Rome, chained to their seats while they rowed long galley boats or ships on the Mediterranean Sea. The next forward step was made by the Romans, introducing paddle wheels in place of oars. These paddles were sometimes driven round by men, but oxen and horses were employed also. This form of paddle ship was renewed in modern times for ferry boats. A Scotchman, Miller by name, made many experiments with paddle ships of this kind, but he found that the men were very easily exhausted, while the use of animals was not very convenient. It occurred to him that the then recently invented steam engine of James Watt might be made to drive the paddles round. It so happened about this time, 1786, Miller heard of a model steam carriage being exhibited in Edinburgh by James Symington, a mining engineer. Miller found that Symington was of opinion that the steam engine which he was exhibiting would be quite as suitable for turning the paddle wheels of a ship as the ordinary wheels of a carriage. Of course, it seems ridiculous to us that anyone would doubt such a simple fact, but we must remember that we have grown up among these inventions. Symington agreed to build an engine for Miller, and by the end of 1788, all was ready for the trial trip on an inland loch. It is interesting to note that the great bard of Scotland, Robert Burns, was one of the 5 passengers on board this first steamship on her maiden voyage across the little loch. But even Burns's clear mind did not foresee the importance of the event. He has left no verse concerning it. Personally, I think this shows Burns's wisdom. The whole affair was so novel that he would not wish to express what might remain a permanent opinion concerning its future. In the preceding chapter, we saw how foolish early critics of the steam locomotive appear to us now. Symington made further experiments with a larger boat on the Forth and Clyde Canal, which crosses Scotland from east to west. This larger boat attained a speed of 7 miles an hour, but it was so lightly built that it could not stand many trips. Miller was supplying the funds for these experiments, and finding this a heavy drain upon his purse, he abandoned it. Symington was an enthusiast, and he got a Scottish nobleman to provide £3,000 for the building of a stronger ship to be used on the canal as a steam tug. This boat proved a success, but at its trial trip it was declared that its wash would injure the whole banks of the canal, and so the vessel did not come into use as a tug. There is something pathetic about Symington having to abandon his great scheme after he had proved that his ship could steam against a strong wind, against which no other vessel could make headway, and at the same time pulling along 2 vessels of 70 tons each. If Symington had suggested that they should strengthen the banks of the canal to suit his steamer, he would have been laughed out of court. Indeed, it would have seemed to them just as ridiculous as the little boy asking the keeper at the zoological gardens if a currant out of his bun would hurt the elephant. When our old clerical friend Dr. Cartwright lost his fortune, in his heroic efforts to establish weaving by machinery, he went to London to earn a living by his pen. Even then he was always busy with some ideas concerning mechanical affairs. He used to discuss the problem of steam navigation with a young American artist, Robert Fulton, who was a constant visitor at the doctor's London house. The indigenous clergyman made a model of a paddle steamer, which was driven by means of clockwork, and which he gave as a toy to a little fellow who became afterwards the great statesman Lord John Russell. No experiments were attempted with steam, but Fulton was keenly interested in the subject of steamships, of the future of which he and Dr. Cartwright were enthusiastic. Some years later, when Fulton was on a visit to Scotland, he got an introduction to Symington, who was most generous in giving full particulars of his ship, and in giving Fulton a trip on board his boat on the canal. It should be mentioned that Fulton told Symington quite frankly that he intended building a steamship as soon as he returned to America. Fulton's American friends laughed at his scheme and spoke of it as Fulton's folly. No one would risk a penny on such ridiculous undertaking. Although Fulton received no encouragement from anyone, he plodded along, and having got his first vessel launched, he proved that he was no madman. We have grown up among steamships, so that it is difficult to realize the great surprise of those who witnessed this new invention. Fulton's biographer tells us that when the steamer came along the River Hudson at night, breathing out flames and smoke, and defying the winds and the tide, the crews of the sailing ships were so alarmed at the approach of this monster that some of them took to their small boats and pulled for the shore, while others fell upon the decks and prayed for protection against the approach of the horrible monster. The flames would be rather alarming, as the fuel was pine wood, which, when stirred by the stoker, would send forth great showers of flaming sparks. Then the usual throb of the paddles, coming through the darkness, would seem uncanny. Fulton's pioneer steamer, Claremont, became a regular passenger steamer between Albany and New York, and other steamers soon followed. It is interesting to consider what happened in Great Britain after Symington was forced to abandon his scheme. A Glasgow carpenter, Henry Bell, had been keenly interested in the subject of ship propulsion, and it happened that Bell accompanied the young American artist, Robert Fulton, on his visit to Symington in Edinburgh. Bell and Fulton kept up a correspondence, but it occurred to Bell that instead of passing on all his opinions to America, he ought to make a practical experiment in his own country. About this time, Bell became proprietor of an inn at Helensburgh, on the banks of the River Clyde. While there, he made some experiments with paddle boats driven by hand, and then sought to introduce a steam engine to turn the paddles. His mad scheme became a standing joke on the Clyde, but Bell also was an enthusiast. When Bell had succeeded with a small boat of 25 tons and 4 horsepower, he placed it on the Clyde to carry passengers between Glasgow and Helensburgh, a distance of about 20 miles. But the canny Scots were very slow to trust themselves in Bell's steamer, the Comet. Footnote: Henry Bell's Comet was built in Scotland about 5 years after Fulton's Claremont in America, and about 23 years after Symington's first steamer referred to in the text. The late Lord Kelvin used to tell how his father and a party of fellow students, after landing at Greenock from Ireland, were walking to Glasgow to attend the opening of the university session, 1813, when on their way they saw a prodigy, a black chimney moving rapidly beyond a field on the left-hand side of their road. They jumped the fence, ran across the field, and saw to their astonishment Henry Bell's Comet, then not a year old, traveling on the Clyde between Greenock and Glasgow. End footnote. The owners of the stagecoaches and sailing vessels spread evil reports about the Comet, but when it had run without accident for some time, the tourists began to patronize it, and Bell was encouraged to try his vessel on the open sea around the coast. Unfortunately, the little vessel was not strong enough for this and was wrecked. A second vessel was burned, leaving Bell in money difficulties. By this time, rivals were building steamers, and against these capitalists, poor Bell had no chance, so that he sank into poverty. Subscriptions were raised among friends, and with a small annuity from the Clyde trustees, Bell was kept from starving. But today, the great shipping enterprises on the Clyde stand as a momentum to Bell's pioneer work. The general principle of shipbuilding has not altered much since the days of the Roman galleys rowed by slaves. These ships had wooden ribs to which the wooden shell was fixed, while the seats for the rowers acted as crossbeams to strengthen the ship. People were content with wooden ships until the invention of heavy guns, whereupon the French government protected some of their wooden warships with a covering or coat of iron plates. Then the struggle began between the gun makers and the shipbuilders. The former made guns which could pierce the iron plating. Then the shipbuilders put on heavier iron plates, and so on they went. At first, the ships always had wooden lining to the iron, and in some cases an inner lining of iron also. When ships built entirely of iron were tried in 1863, they came into general use very quickly. One might think that an iron ship would weigh a great deal more than a wooden ship of the same size, but as a matter of fact an iron ship is much lighter, for the required strength is obtained with very much thinner walls. It will be of some interest to see how the modern shipbuilder sets to work and we shall suppose that he is going to build one of those gigantic liners or a warship such as shown entering the water in the illustration facing page 310. The preparatory work of drawing and making blueprints from the tracings is very much the same as has been described in the preceding chapter on locomotives, but there is one important difference in carrying the design into operation. The locomotive builder made a full-size template of the whole frame of his locomotive, but it goes without saying that the shipbuilder is not going to make a full-size template of a ship. Leaving the size out of account altogether, it must be apparent that the conditions are entirely different. The side of a ship is not a piece of flat metal. It bulges out from the keel to the deck and from the bow to the stern. We speak of the beautiful lines of a modern ship. It is obvious that it will be the formation of the ribs of the ship which will determine the lines. If the ribs of a ship were merely straight pieces of iron bent at certain angles, the shipbuilder could work from a small drawing, and just make the ribs so many times larger than those in the drawing. He might use that simple plan even if the ribs were bent in semicircles. But to get all the different complex curves of hundreds of ribs required to produce the shape from bow to stern by merely multiplying the lines of a small drawing is quite out of the question. The matter would be simplified if the shipbuilder could draw his ship full size upon a blackboard. This suggestion may seem rather absurd when one considers the size of an Atlantic liner or a battleship, but that is what the shipbuilder really does. He would require a great ladder to get up to the blackboard of such dimensions, so he lays it on the floor. Indeed, he makes the blackened floor of an immense room serve as a blackboard, this room being known as the mold loft. Having chalked off a profile or a side view of the ship's hull, see figure 16, he draws also a body plan, or what one might describe as the ship's waist measurement, at different points. Then he draws a bird's eye view or plan of the ship, or a half-breadth plan is sufficient, as the ship is equal-sided. With these three chalk drawings, the builder arrives at the curves of the full-sized ribs. He bends a piece of flexible wood into the form required, and then chalks the shape of the rib upon the floor. But how are the workmen to get those chalk drawings away with them to the works? They must bring the floor of their own workshop up to the mold loft, and have shapes of the ribs transferred to it. Of course, the workmen have to take their floor to pieces to carry it, but the planks are placed in their proper positions on the mold loft, and the shapes of the ribs are drawn on with a sharp knife, as chalk marks would be too easily erased. The largest rib is cut, or screeved, first of all, then the next in size is placed within that, and so on. The planks of this screeved floor are carried back to the workmen's quarters, where the floor is relaid. Before the workmen can bend the steel bars, or angles, into shape, bars must be raised to a white heat. It is obvious that these white-hot angle bars cannot be brought onto this wooden floor upon which the forms of the ribs have been screeved, but a very convenient plan is adopted. When considering the manufacture of iron, we saw that if all the carbon were burnt out of the iron, the remaining pure iron was so soft as to be useless for most purposes. This soft or very malleable iron comes in very conveniently for making patterns or templates of these curved ribs. The cold metal bars are bent with ease to conform with the curved lines representing the ribs. When the soft iron bar has been bent into the form of a rib, it is taken over to a heavy cast iron floor, which is riddled with holes or sockets in which metal pegs may be placed. A row of these pegs is arranged around the curved line of this soft iron template, so as to fix it firmly in position, and the red-hot angle bar, which is to form the real rib, is brought out of a long furnace and bent against the template. It is then clamped down in position by a second row of pegs, arranged along its other edge, and it is held in this position until it has cooled. In another part of the busy works, steel plates are being prepared to form the shell of the ship. In most cases, these are less than 1 inch in thickness, but it is no light task to make about 500 holes around each plate, for the purpose of riveting the plates together. There will be somewhere about 10 million holes to be made in the plates of an Atlantic liner. It would take a man a long time to drill one hole by hand in a solid plate of steel, and even to drill such a number of holes by machinery would occupy too much time. The shipbuilder saves time by having very powerful machines, which punch a hole right through the plate with a single downward stroke. Of course, it requires considerable energy to push a blunt metal tool straight through a heavy sheet of solid metal, but these punching machines are quite equal to the task. There are large machines for rolling the plates, while other machines shear and joggle the edge so that the plates will be of correct size and overlap properly. The prepared ironwork all makes its way to the yard in which the ship is to be erected. The first thing is to lay the keel. When some of us were boys, our one idea of a keel was a heavy piece of lead or iron shaped so as to project downwards from the ship. But the keel of a modern liner might be described as a long gutter made of heavy steel plates. Toward the middle part of the ship, this long gutter arrangement is only slightly bent. In other words, it is like a broad, shallow gutter. While towards the bow and the stern, it takes the form of a deep and narrow gutter. Along the center of this flat keel plate is set up the vertical keel plate, which is just like a heavy girder. These two parts are well riveted together, while the base of each rib is also riveted to these two parts, which form the keel. After the skeleton of the ship is set up with its full complement of ribs, crossbeams, and bulkheads, or transverse walls, all in position, the ship is plated. Most of the riveting is still done by hand, although there are mechanical riveters, powerful hydraulic riveters being used for very heavy work. In the old days of wooden ships, the seams of the planks forming the shell had to be caulked with tow or yarn to make them watertight. And in the modern steel ship, we find compressed air machines busy caulking the seams of the steel plates by hammering the edges of the plates. In order to prepare all the woodwork and other fittings for the interior of the ship, a large number of carpenters, joiners, blacksmiths, plumbers, electricians, riggers, mechanics, coppersmiths, painters, and so on are employed. In the joiners department, we find complete cabins fitted up, so that the ship owner may see exactly what the builder proposes to make for the ship. To return to the outdoor work, we can see that it has been a comparatively easy thing to lift the different parts of the ship and place them in position. But when these have been joined into one huge piece to form the ship, the total weight may be anything up to 16,000 tons, which is not a weight to be moved easily. Great care must be taken to see that the builder will have no difficulty in launching his ship when ready. The builder is not going to supply the energy to take his ship into the river. He depends on the fact that one mass of matter attracts another mass, and that the earth, being so very much greater than any object upon it, possesses an overwhelmingly predominant position in the question of attraction. The builder takes care to build his ship on a declivity sloping down towards the river. He must not make the decline too great, or the ship could not be properly launched. Careful calculations are necessary to arrive at the exact declivity required for any particular ship. The keel is laid upon piles of wooden blocks, the height of each successive pile increasing towards the bow. If one walks underneath the middle part of the great liner, one is impressed with the flatness of the bottom. Indeed, it is as if one were under a great flat roof. I mention this in case anyone should imagine that the stilts or supports placed against the sides of the ship are maintaining a very delicate balance. When the ship is ready for launching, the keel blocks are removed and the vessel is allowed to rest on a pair of wooden rails, or ways, which run parallel to one another and form a wide track. Needless to say, the builder is not going to let his fine ship scrape along on these fixed ways. He gives the ship a wooden toboggan, as it were, upon which she can ride safely down the fixed ways. These moving ways are heavy beams of wood which rest upon the fixed ways. It is upon the moving ways that the ship rests when being launched. There is no need to strap the vessel to this simple toboggan, for her great weight pressing upon the wood beams is just as good. If the moving ways were laid merely upon the top of the fixed ways, the ship's weight would cause so much friction between the surfaces of the two wooden beams that the vessel would remain securely in the one position. But if a liberal supply of heavy grease is placed between the two surfaces, the friction is reduced so greatly that the moving ways slide down the fixed ways and carry the heavy ship on their back. Of course, those greased ways are raised into position, pressing upon the bottom of the vessel before the piles of keel blocks are knocked away. The ship, while resting upon the prepared ways, must be held back from gliding down the hill before the time comes. When the launching ceremony has been performed, 2 large trigger arrangements, one on each way, are released, and the great ship is pulled down the hill by gravity, dragging heavy anchor chains with her, and safely launched into the river or into the sea. In order to make the launching ceremony as complete as possible, the pressing of an electric push may be arranged to switch on an electric current which releases the trigger arrangements. In the illustration facing page 310, we see the launching of HMS Indomitable from the yard of the Fairfield Shipping and Engineering Company, Ltd., at Govan, just below Glasgow, on the River Clyde. End of Chapter 24, read by Timothy Osink, West Jordan, Utah, March 30th, 2023.
Chapter 25 of the Romance of Modern Manufacture. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Larry Wilson. The Romance of Modern Manufacture by Charles R. Gibson. Conclusion. When considering the great achievements of modern machinery, we should remember that the ancients could produce excellent specimens of manufactures, but at what an enormous cost of labor! And when admiring the great tools which we use in some modern industries, we should keep in mind the fact that the ancients could carry out immense undertakings without these aids. Witness the great pyramids and Sphinx of Egypt. But the building of these must have taken an enormous amount of human effort. Indeed, it is stated that one pyramid took the continuous efforts of 100,000 men for about 50 years. In this connection, it is interesting to note the following statement, which I have extracted from an old book entitled Mathematical Magic, written about 260 years ago. After referring to the pyramids, the writer says, "Above all ancient designs, that would have been most wonderful, which a Grecian architect did propound unto Alexander, to cut the mountain Athos into the form of a statue, which in his right hand should hold a town capable of 10,000 men, and in his left a vessel to receive all the water that flowed from the several springs in the mountain. But whether Alexander in his ambition did fear that such an idol should have more honor than he himself, or whether in his good husbandry he thought that such a microcosm, if I may so style it, would have cost him almost as much as the conquering of this great world, or whatever else was the reason, he refused to attempt it. We have direct evidence that the ancients were able to handle huge pieces of stone weighing in one case at least as much as 380 tons. Our largest crane today cannot lift half of that great weight. But what an enormous amount of human energy the ancients must have expended. In the preceding chapter we have seen to what a great extent automatic machinery has relieved man of much manual labor, and enabled him to produce necessary articles and even luxuries at a cost which brings them within the reach of almost everyone. There is a true romance in the fact that much of the monotonous toil of man has been taken off his shoulders by inanimate machines of his own invention. It is obvious that the introduction of machinery into many branches of industry has meant hardships for some particular generation of toilers, and we must consider these as martyrs in a good cause, the general advancement of mankind. One fact which is very prominent in the preceding pages is that the real inventor very often suffered martyrdom on account of his zeal. To take only one or two instances, James Watt suffered much in his endeavors to produce a practical steam engine. It was with a sore heart and a worried mind that Watt wrote, "Of all things in the world there is nothing so foolish as inventing." Fortunately, he reaped financial success before his death, which occurred in the same year as that in which the late Queen Victoria was born, 1819. We have seen that Hargreaves and Crompton both died penniless and broken-hearted, though by that time many manufacturers were making money by means of these inventors' machines. We have also seen how Lee, the Cambridge clergyman who invented knitting by machinery, met with no encouragement, and died of a broken heart in Paris. Today many thousands of people receive handsome dividends earned by factories employing such machinery. Then we recollect the hardships of poor Elias Howe, the American mechanic who invented the sewing machine, and again how poor Palissy, the potter, broke up his household effects in order to feed his furnace during his last desperate experiment. These are but a few of the martyrs who have sacrificed themselves in laying the foundations of our modern manufactures. When people are discussing the position of Great Britain as a manufacturing nation, one often hears the question of technical education brought forward as a reason why continental countries, more especially Germany, can excel Great Britain in certain industries. One is apt to think of this as a problem of recent date, but that is not the case. In the old book, 1648, to which I have referred in the opening paragraphs of this chapter, there appears the following sentence: "Ramus hath observed that the reason why Germany hath been so eminent for mechanical inventions is because there have been public lectures of this kind instituted amongst them, and those not only in the learned languages, but also in the vulgar tongue, for the capacity of every unlettered ingenious artificer." These words were written more than 260 years ago. Great Britain has wakened up to the fact that technical colleges are an absolute necessity, and many of our modern colleges are excellent examples of what is required. Another conclusion at which one may arrive after considering the methods of manufacture in different industries is that there is a great similarity between the actions of the machines used for different purposes. We can still divide all motions into the 4 divisions set forth by Aristotle, the tutor of Alexander the Great, more than 2,000 years ago. These were described as pulsio, tractio, vectio, vertigo, which signified thrusting, drawing, carrying, turning. A friend has remarked to me that we have become so accustomed to having things done for us by machinery that one might almost be surprised to hear that any action could not be performed by a machine. He suggested that we might even make machines to wash our faces. I have distant recollections, however, of an automatic boot-black which was set up at one of our large railway stations. I was foolhardy enough to let the machine brush my boots on one occasion, but on making inquiries some time later I was informed that the automaton had been dismissed, and the human boot-black confided to me that it had nearly taken the feet off the gentleman. Even if it were possible to get machines to perform all manufacturing operations, there would still be plenty for a man to do. To manufacture articles of necessity and luxury, to distribute these and carry them all over the world, is not the only possible interest in life. Indeed, there are many of us who are convinced that if every young man would take up a definite hobby, apart from his daily work, our country would be the better for it. There is too much idling away of time by the modern youth, and Cooper's words are still true. An idler is a watch that wants both hands, as useless if it goes as if it stands. And again we have the words of Ben Jonson: "Virtue, though chained to earth, will still live free, and hell itself must yield to industry. End of chapter 25. End of the Romance of Modern Manufacture by Charles R. Gibson.